transportation. In this presentation, I'm going to be talking about the different forms and different methods of transportation using electricity and magnetism and the more theoretical uses of electricity and magnetism in the world today. Why is electricity and magnetism important for future transportation? Well, there's a lot of benefits in switching to using electricity and magnetism for transporting around the world, but one of the main ones is helping the Earth become less polluted. Also, fuel-based energy is no longer cheap because we're outsourcing a lot of gas coming in from other countries. It's starting to cost a lot of money. Traveling could also be faster and safer, and there's less automobile maintenance every year with electric cars rather than gas-powered vehicles. So using electricity and magnetism, we can not only stop the pollution in our atmosphere, but we can find easier and cheaper methods of transportation. The first piece of technology that I'm going to talk about is maglev trains. Maglev stands for magnetic levitation trains. So these trains use the simple law that, unlike magnets, repel each other. So by switching the wheels for magnets, the train is free to travel without any friction slowing it down. The repelling magnets are the train's superconducting magnets and the magnetic coils along the guide rails for the train. These rails are shaped in a U that kind of surround the train to make sure it doesn't go off the rails or anything like that. The opposing magnets with alternating north and south poles creates kind of a push-pull effect that propels the train forward. The train you see below is located in Japan and broke the world record for traveling 366 miles an hour. How will maglev trains benefit society? Maglev trains will benefit society by being better for the environment because they don't release any emissions, no CO2 in our atmosphere. They're also faster than traditional trains. Like I stated before, trains traveling at 400 miles an hour is a little bit faster than the trains we have today. There's a lot of business involved in these trains because it's going to develop more jobs, more opportunities, and more revenue to the cities that have them. Also safer, because there's not as much combustion involved with electrical engineering, and just a simple advancement of physics and engineering is going to allow physicists and engineers to produce more and better trains like this to improve transportation all around the world. This is one of the more theoretical uses of magnets for transportation: roads for self-driving cars. Volvo completed a research project for their self-driving cars with magnetic sensors implanted in the roads that the car was driving on, and it gave it better navigation, better control, and was able to detect when it was going in and out of lanes better than the self-driving cars today. And this was a good application for magnetic sensors, but the practical use, however, is not going to apply to the real world, because ripping out all the roads we have now is just too much money, and it's not going to be worth it because there's not that many self-driving cars on the road today. The cons outweigh the pros for the roads for self-driving cars. The project would be an awesome advancement for the use of self-driving cars and help them navigate better through the city, but it's a little bit too much money to restructure all the roads we already have. And also, construction during this project would be awful and make everyone's commute harder, and power outages could even lead to accidents, because if the power goes out and the magnetic sensors go out and you're using your self-driving car, you might run off the road because the magnetic sensors are clicked off. So it's a good concept for magnetic sensors, but I don't think it'll apply to the real world anytime soon. Electric cars are probably the most used and most relevant piece of electrical engineering in the world today. Electric cars have been around for the past decade. Companies like Tesla and Volvo have been making extreme advances in the field of electric cars. They're increasing the battery strength. You're able to go farther on a single charge than you ever have. And this is really beneficial to people who travel every day because it also produces little to no pollution since they're powered by electrical energy. And most electric cars can travel up to 70 to 100 miles on a single charge, and some of them with that extra charging capacity can travel for 265 miles. So they're going to keep upgrading these cars, and these cars are going to be able to go farther and farther on a single charge, which will be cheap, it'll be efficient, and it'll be better for the everyday user rather than gasoline-powered cars. The physics behind electric cars are actually pretty simple. The energy from the rechargeable battery is connected to the motor, which converts that electrical energy to mechanical energy to make the car move around. Like normal gas-powered vehicles, if you push harder on the accelerator, the more energy will be used. And electric cars have pretty good acceleration because that conversion of electrical to mechanical energy is actually really fast. And they're also cheaper because they're idle-off or regenerative braking features. Idle-off is where your car will kind of shut off when you're stopped to save that battery and save the juice that's in your car so you can go farther. And regenerative braking, when you're braking, the car actually recharges the battery, so you're able to go even farther. And the average car battery is about 24 kilowatts, and to fully charge that battery is only $2.50. So it's way cheaper than the average $20, $30, $50 to charge or to fill your gas tank in the cars we have today. The Hyperloop transportation system is a theoretical system of transportation developed first by Elon Musk. He is the owner of Tesla auto manufacturers. And in this Hyperloop transportation, they use a different type of magnetic levitation they call passive. So the passive maglev is a little bit different than the regular maglev used in Japan or Europe. The passive maglev uses unpowered loops of wires in the tracks and then room temperature magnets in the train pod, unlike the ones in Japan or Europe. Regular maglev trains, they do require very expensive infrastructure, and the power supplies need to be located at each interval on the track because they do use a lot of energy. Passive maglev was created by late physicist Richard Post in the year 2000. He called his new system the induct track. How does the induct track work? Under each train car, there is a flat rectangular array of magnetic bars called the Hallback array. The bars are placed so the magnetic orientation of these bars are at the right angle of the adjacent bars. So what this does is it creates a strong magnetic field below the array, and above the array the field lines cancel out. The track has closely packed insulated wires, and it produces levitation by inducing electrical currents within the track. As Faraday discovered in 1831, moving a permanent magnet near a loop of wire will induce a current in that flow, or to flow in that wire. As long as the train is moving faster than a few kilometers per hour, the train will be levitated a few centimeters because of those currents being induced in the wires. Deceleration will be achieved by reversing the thrust force, and regenerative braking will recharge the battery. Just like we said earlier with the electric cars, the Hyperloop track is going to have the same type of technology where its battery will be recharged by the process of regenerative braking. Another theoretical use for magnetic propulsion is the magnetic slot car. The slot car idea was created by German designer Christian Forg, and Forg suggested a plan for placing electric motors underneath the roads, specifically the highways. He called it the Speedway Transport System, and it involved placing a network of linear electric motors to propel electric vehicles along the highway. He sees our future electric vehicles as kind of a dual mode design, one for city travel and one for highway or long distance traveling. And the brilliance behind his design is that normal cars can still drive on these roads that would have the linear electric motors, but only the electric cars would be able to be propelled by these electric motors even without the driver actually controlling the car itself. These linear motors could actually propel the car and control the car on their own. How would the magnetic slot car system work? The futuristic dual-mode electric vehicle that Ford designed had the two settings, one for city travel and another one for long-distance travel. The city travel would be controlled by the internal electric motor of the car, just like electric vehicles today. If you look down at the bottom of your screen, you'll see the two different modes, and you'll notice that they're a little bit different. The short range is more upright, and the long range is leaned down a little bit. And why Ford did that is because he wanted that highway electric vehicle to be a little bit more aerodynamic, so it was easier for the external linear motors to propel the car across a long distance. And how the vehicles would be propelled is by the opposing magnetic forces in the linear motor system and the electric vehicle's conductor. In conclusion, the examples I discussed in this presentation, like the magnetic slot car, the hyperloop transportation, and the advances in the electric car, are all terrific improvements to our future transportation using electrical or magnetic means to get from A to B. Physicists all around the world are going to continue developing new methods of travel using these forms of energy, and it is our job to keep our minds open to these new forms of energy and transportation and to stop the use of fossil fuels. Future transportation can not only be cheaper, but it can be better for the environment as well. Thank you for listening to the presentation. I hope you learned something.